All right, we talked last time about this whole little morning session thing. For the first 4 or 5 of them is going to be about atomic structure and radiation. And it was about in the early 1900s, late 1800s when people like Becquerel and Curie started figuring out what radiation was. And then a little bit after them came along Rutherford. And Rutherford essentially took a box, a lead box that looked like this, and he bored a hole in the piece of lead, and then he put some kind of radioactive element in here in the bottom of the hole. He shot that in a beam through either a magnetic field or an electrical field. And what he was able to figure out, because he had some kind of photographic plate over here, is that when it went through this electricity, it separated. Parts of that radioactive beam went toward the positive plate. Part went toward the negative. Part didn't seem to be affected at all. So he called those 3 kinds of radiation alpha. Alpha were the ones attracted to the negative plate. Beta, those were the ones attracted to the positive plate. And then what's that symbol in the middle? Gamma. Okay? And gamma weren't affected because they weren't charged. They were uncharged. We know today gamma rays are what? Well, they're dangerous, but what are they made out of? No particles. They're just a high energy form of light, essentially. No particles. The other 2 are made of particles. Beta particles are negatively charged particles. That's why they're attracted to the positive. And alpha particles are negatively charged. No, it's backwards. Alpha particles are positively charged particles because they're attracted to a negative plate. So, went a little further. A little bit later came scientist J.J. Thomson, trying to figure out what an atom was made out of. And he came up with what he called his plum pudding model. His idea was that most of an atom was this solid mass of positive charge, sort of like pudding. And that embedded in that positive pudding were these little negative electrons. And that was the model that we thought was true for a long time. A little bit later, again, Rutherford comes along in 1911, and he does the famous gold foil experiment. What he did is he took a piece of gold foil, thin gold metal. He used his little lead block with radioactive stuff in it again, and he shot a beam of alpha particles through the gold foil. What he expected, if Thomson's model was correct, what would you expect? You'd expect something to bounce off. But most of it went straight through. So Rutherford concluded that most of an atom's made of what? Space. Most of it atom's space. But there were some cases when he got these huge deflections, like the alpha particles way over here, and the alpha particles way over here. So he decided that most of the mass of an atom is concentrated in a really tiny way. Nucleus. And that nucleus is what charged? Positive, because alpha particles are positive. If they got close to that positively charged nucleus, that's when they got deflected. So Rutherford, this experiment led us to a different model of the atom. Again, he concluded that most of an atom was empty space. Most of the mass is densely packed in that positive nucleus. And Rutherford thought the electrons orbited the nucleus like planets orbited the stars. He was wrong on that. One thing this model couldn't do was account for the different kinds of light that atoms emitted when they were excited, when they were given electricity. That's what Rutherford's model would look like, and that's still the model you sometimes see in textbooks, right? It leads you to believe that electrons are orbiting like planets. Yeah. Lots of times. I can't give you a number, but it's been replicated a lot of times. Cool experiment. All right, in 1913, Niels Bohr comes along. And he was trying to explain some of the problems with Rutherford's model in terms of what he called quantum mechanics. It's a new field at that point in time. What's a quantum? Yeah, it's a certain size pack of energy, right? Quantum mechanics basically says that energy only comes in certain size packs. And either you can take the whole pack or you can't take what? You can't take any. You take the whole thing or you don't take any. All right, what Rutherford wanted to explain were some of these problems with the Rutherford model, Bohr rather. He found that electrons don't emit electromagnetic radiation while in a given orbit or energy level. They only give off energy when they're what? When they're going from a higher level back down to a lower level. That's when they give off the energy. The electrons can't stay in some arbitrary energy state. They always want to get back to what? The ground state. And those energy levels are quantized. For example, a piece of steel can only absorb certain kinds of light, right? Everything else gets reflected off. Also, electrons emit electromagnetic radiation when they make transitions from high energy levels to low energy levels, from an excited state down to a ground state. And how can they be excited? What kinds of things can excite them? Heat or electricity, like in a fluorescent light bulb, for example. And the energy that they give off, the kind of light that they give off, the photons that they emit, and you guys all know the word photon, right? Pack of light. The energy in that photon is equal to the energy difference between the two levels that they move between. Now this is an energy level diagram for hydrogen. And we'll be coming back to this a lot here in a minute. But these numbers over here on the right, let's go all the way down. Those are the energy values an electron has when it's in those energy levels, in electron volts, which are these tiny units of energy. So if an electron jumped from energy level 2 down to energy level 1, how much energy is given off? If it jumped from here down to there, how much energy is given off? The way you do it is you take the initial energy level, which is negative 3.4, and you subtract from it the final level. So it'll be negative 3.4 minus 13.6. So you end up with around 10, right? 10.2 would be given off. All right, now let's get to a little math. This is where it's going to be some math you may not have seen before. Like I said before, the energy for an emitted photon is given by this equation. Actually, the energy given off for the photon is the energy initial minus the energy final. Up here, here's something else we can calculate. A little f tends to stand for frequency. We can calculate the frequency of light given off by using this equation. Energy initial minus energy final, all divided by little h. And little h is Planck's constant, which is this number right here. What does the frequency of light tell us about the light? If we know the frequency, what do we know? We know the color. And we can also, it's also related to the amount of energy that it contains. We can also go down, and we can use this equation right here to help us find what else? The wavelength. That funny little upside down Y thing is called what? Lambda, and it's for wavelength. And what's C? C is the speed of light, which is 3 times 10 to the 8, if you don't know that, meters per second. one other thing you need to know, remember that chart that we saw for hydrogen was giving us the energy values in electron volts. We need to be working in joules in these equations. So this will let you convert between the two. 1 electron volt is 1.6 times 10 to the minus 19 joules. And by the way, on the AP physics exam, you will have a table of constants that you can use. So you're not expected to memorize all these constants. You'll have that value. So the first thing we're going to do, if we know that, say, well, let's just work a problem. Let's say we wanted to work this problem. Give the frequency and the wavelength of a photon emitted when an electron makes a transition in a hydrogen atom from level 5 to level 3. So let's go back to that chart. What's the first thing we need to know from the chart? The energy at 5 and the energy at 3. So at 5, you guys help me remember this. Negative 0.54, and at 3, negative 1.51. So 5, negative 0.54, negative 1.51, right? All right, like we said, first of all, we need to calculate the difference in energies. We take the initial one minus the final one. Subtract that out. I did something wrong here, right? Because it's minus a minus. So it should be a plus. So the difference in energy is 0.97 electron volts. But like I said before, we don't need this in electron volts, we need it in joules. So we've got to use that conversion. And the conversion is 1 electron volt, and I've got it written over here on the board so you can see it. 1 electron volt is 1.6 times 10 to the negative 19 joules. So we do the math on that. So that's 1.552. I'm going to write that down up here. 1.552 times 10 to the minus 19 joules. So that's the amount of energy released when that electron jumps from 5 down to 3. That's the energy of the photon. Now I'm going to erase some of this for a second. And remember, the next equation that we had on our list a second ago was to find the frequency. And the way to calculate the frequency was take the energy difference, which we've got, and divide it by what? Planck's constant. So energy difference divided by h, Planck's constant. I also wrote h down up there on the board for you. 6.6206. I never remember those last digits either. Which is a 6, I don't know. 6.626069 times 10 to the minus 34. Now I want to work on the units here for a minute. The units for Planck's constant, meters squared, kilograms, over seconds. Now remember, our energy up here, it's in what units? Joules. Now, we'll learn a lot more about how to deal with these units later on in this class, but a joule is actually equal to a Newton times a meter. Yeah, and a Newton is equal to a kilogram times a meter over a second squared. So these units are going to show us something. Because here's really a joule we can write this way. Kilogram, meter, per second squared. That's a Newton times another meter. And now if you look at what happens with the units, meters squared cancel out with those 2 meters. Kilograms cancel. We got seconds squared and seconds. One of those cancel. So the unit we're left with is 1 over a second. Nothing over a second. What is that unit? It's per second. This was the second squared. We're down here on the bottom. So that's this second cancels to that, and we're just left with nothing over seconds. That's hertz. Something per second. We're looking for frequency, right? So that makes sense. That's what we need is hertz. So if we do the math on this, 1.552 times 10 to the negative 19 divided by 6.6260697 times 10 to the 34 negative. We end up with 2.34. And I'm just going to round it there, times 10 to the 14th hertz. Sometimes you'll see hertz written HZ. Sometimes you'll see it written like this. S to the minus 1, which means it's under the bottom of the fraction, right? It's per second. So that's the first thing we wanted was the frequency. We could go to a table of light and we could figure out what color light that is. We're not going to do that right now, though. We also, though, want to find the wavelength. Remember, the way that we're going to calculate the wavelength is C equals wavelength times frequency. So we've got, if we rearrange, wavelength would equal speed of light divided by frequency. And for our purposes, speed of light, we're going to use 3 times 10 to the 8th meters per second. And we're dividing that by the frequency, 2.34 times 10 to the 14th hertz. Those seconds are going to cancel. Makes sense because we're looking for wavelength, right? We ought to get something in meters. So it's 3 times 10 to the 8th divided by, I left off my power here, by the way. This is 14 power. 3 times 10 to the 8th divided by 2.34 times 10 to the 14th. And we end up with a wavelength of 1.28 times 10 to the minus 6 meters. Make sense? Yeah, because this would be like, you would have meters per second over 1 times seconds. So you have to invert and multiply, and the seconds cancel out. Everybody okay with that? Yep. So essentially, well, we'll do another problem in a minute. A couple other quick points. In the field of quantum mechanics, dealing with these packets of energy, an electron only transitions from lower to higher levels when it absorbs a photon with an energy value equal to the difference of the energies between the energy levels. Now let's think about that for a minute. There's a lot of words there. If we had, say, an electron in a piece of iron, that electron can only move up if the right kind of light hits it, right? Light with a certain amount of energy that's equal to the amount of energy between the difference between this energy level and the next one up. Or the next one up. It could jump, it could skip one, right? Let's say that, I'm just going to make up some levels here, but let's say energy level 1, energy level 2, energy level 3, energy level 4. Let's say that this difference was, and I'm just making up numbers here, 20 electron volts. And the difference between here and here was, say, 10 electron volts. And the difference between here and here was, let's say, 5 electron volts. If light got shined on this atom down here, and the energy of the light per photon was 35 electron volts, could that atom absorb that? Yeah, and that would make the electron do what? Jump from 1 up to 4. Yeah.
Well, if it's like 36, we go up to 4 and stop.
If it's 36, it can't even absorb it. It bounces off. It's reflecting, which is why this is happening up here on this sink. You see all that reflection. That light is being reflected. It can't absorb because it doesn't fit.
If it's like reverse energy level, like if there was like 21, it still could go up.
It can't absorb it. If it's 21, it's going to reflect it off. It's got to be 20. All or nothing. That's kind of what the idea of a quantum is. It's all or nothing. Either you can take it all, or you can't take any of it. Does that make sense? That's the idea of quantum mechanics. You take all the energy, or you can't take any of it. All right, I'm not going to deal too much with this. Did you guys talk about the Schrodinger equation in AP Chemistry? We're not going to do much with it in here either. Schrodinger equation is one of those things, kind of like a lot of that Einstein stuff. It'll give you a headache if you talk about it for too long. The Bohr model only worked well for hydrogen and really small atoms. The problems we just did, those work perfectly for really small atoms. But things get more complicated when you start moving up to the bigger atoms. And you got all those electrons swirling all over the place. A guy named Schrodinger came along in 1926. And he came up with a mathematical function to let us do some of these calculations. His ideas basically eventually led to what we call the electron cloud model. The electrons are in this cloud, and instead of trying to figure out exactly which level they're in, you calculate the probability that they would be in this level or the other level. We're not really going to deal with that too much. Do I now? Yeah. We're not going to deal too much with that for right now. Let's look at a couple more problems. First question, how much energy is needed to ionize a hydrogen atom in the n equals 4 state? So let's say that you have an electron in a hydrogen atom in the 4th energy level. That's what that means, n equals 4. What does it mean to ionize it? Make it move. Okay? Make it move up a level, right? So let's go back to our little diagram. In n equals 4, its energy is negative 0.85. Okay. So to make it move up, what do we got to do? To make it move up, we've got to add that much energy. We've got to add 0.85. To make it go up, we've got to add 0.85 more. So the answer is positive 0.85 to this question. That's what I'm trying to tell you. To make it move out of this energy level and make it go up, we've got to add that much energy. Positive 0.85 to make it go up. That would be how much would be given off if it fell from 5 to 4. But to make it leave that energy level, you've got to add 0.85. All right, number 3. Which electron transition will emit a photon with the greatest frequency? Now you might just have to go in and calculate it. We're assuming hydrogen. But if you look at this diagram, you can get by without doing the math if you know anything about light. What forms of light have the highest frequency? UV, right? UV are way down there on the bottom of the electromagnetic spectrum, down there close to what else? Gamma rays and X-rays, right? High frequency, high energy. Notice when you're going from like 6 down to 2, or 5 down to 2, or 4 down to 2, you're getting visible light. You're getting different wavelengths of visible light. But when you transition all the way down to 1, that's when you start getting these UV lights. Because the differences in energy between like 6 and 1 are really what? Really big. And if the energy differences are big, what are you going to get? High frequency. High frequency means big energy. So something down to 1 is going to give us the biggest frequency, right? The highest frequency. Like I said, you could calculate each one out. But if you know that idea, when you're going from something down to 1, you're going to get a really high frequency. Should tell you C. All right, 4. An electron in the ground state of a hydrogen atom can absorb a photon with any of the following energies. Well, let's look. That's one we are going to have to calculate. Let me get some of the writing out of the way so we can see what we're doing better. So if it was going to go from here to here, what we're going to do is basically subtract the difference there, right? So if we went 3.4 negative minus a minus, so plus 13.6. This difference from here to here is about 10.2. We could calculate the difference between here and there. So 1.51 negative plus 13.6. And that is 12.09. Come on in.
Thank you.
We also can calculate the difference between here and here. So negative 0.85 plus 13.6, 12.75. We could also do it from here to there. Negative 0.54 plus 13.6. And that's 13.06. So you guys help me remember those numbers. 12.09, 10.2, 12.75, 13.06. Which one of those is not on the list? B. Yep. All those others were exactly calculated, right? That's a little too much. If it's not exact, it won't happen. All right, this is another one of those frequency questions and wavelength things. So let's look at this one. So this time we're going from 3 to 1. Last time we did what, 5 to 3? Yeah, last time we did 5 to 3. So now we're going to go 3 to 1. I'm going to put in a blank slide so we have plenty of space here. Maybe. All right, so I'm going to back up a couple slides first. We need to know the energy values for energy level 3 and energy level 1. So at 3, negative 1.51. And at 1, negative 13.6. So now if we go back and we try to work this thing, we're trying to find frequency and wavelength. To find frequency, we established that we need the initial energy minus the final energy, all divided by what? H, Planck's constant. So, the initial energy, the energy at level 3 is negative 1.51 electron volts. We want to subtract from that the final energy, which is the energy down there at number 1, which is negative 13.6. So if we do the math on that, $12.09. So our frequency is 12, and actually before I go further, that difference is in electron volts. For this to work, we've got to convert those electron volts over to what? Joules. And remember, we've got the conversion written over there on the board. 1 electron volt is that many joules. So if we do the conversion, here's what we get. I'm going to go ahead and write a joule this way so that we can see the units when we get around to working this. That's what a joule is. And remember to calculate frequency. Frequency is equal to that energy difference divided by Planck's constant, which we also have over there on the board. So now again, we look at our units. The square meters are going to cancel. Kilograms are going to cancel. Everything cancels except 1 over a second, hertz. And if we do the calculation, so 1.93 times 10 to the negative 18 divided by H. We end up with about 2.91 times 10 to the 15th hertz. That's frequency. And then to find wavelength, we'll use C equals wavelength times frequency, which means wavelength equals C divided by F. So it's 3 times 10 to the 8th divided by our frequency. That's an S down there, by the way. Seconds are going to cancel. So it's looking like we get about 1.03 times 10 to the minus 7. And since our seconds cancel out, our wavelength is in meters. Makes sense? All right, we've got time to look at maybe one more question. Let's look at 7. How many different photon frequencies can be emitted if an electron is in an excited state, n equals 4? Let me put in one more slide, blank one. And we will end with this one for today. All right, so let's say we have an electron in energy level 4. It could jump from 4 down to 1, right? And that would give off a certain photon. It could jump from 4 down to 2, and that would give off a different photon. It could jump from 4 down to 3, and that would give off another photon. So right now we got 3. But what else could happen? After it went to 3, then it could go to 2, right? After it went to 2, it could go to 1. After it went to 3, it could instead jump to what? It could jump down to 1. So I think if you count those, you should come up with what? 6. There's 6 different photons that could be given off. That's why if you had a container of hydrogen and you shocked it with electricity, like a neon kind of light, you're not going to get just one color, right? If you look at the spectrum, you're going to get several little spectrum lines, because how many electrons are in that tube of hydrogen? A bunch. A lot of atoms are in that tube of hydrogen, and some of them are going, electrons are jumping 4 to 1, and some are going 4 to 3, and some are going 2 to 1, and so on. You get a mix. And when all those mix together, you get a representative color. For example, with a neon light. What color is a neon light typically? Reddish orange. Always reddish orange. But on the other hand, if you had a bulb filled with, I'm trying to think of the one I know. Argon is kind of bluish, isn't it? I think argon is bluish. each light, each element has a certain color that's usually representative, but it's all those different spectrum lines that add together to give you that one color. It's not that all the atoms are giving off the same color. It's that all the different spectrums that you get add up to be that color. Does that make sense? Good place to stop. Clean up.